In this chapter, chapter 10, which is mechanics, we're going to look at forces and how we can resolve forces. And we'll also have to use some of the SUVAT skills that we learned in the last chapter as well to help us. But rather than looking at quantities like velocity and acceleration and time, here we are focused on forces and also acceleration. Okay. Now, Isaac Newton, I certainly hope you've heard of him. He was rather a prolific mathematician, came up with a pretty big proportion of the things we learn in A-level maths. He was a bit of a physicist as well and came up with these three laws for forces. Now, the first law was that an object will remain at rest or at a constant velocity unless acted on by a net force. So the at rest bit is pretty simple. If you have an object sat on a table or sat on the floor, it's going to remain at rest unless you act on it with some sort of force. That's common sense. The bit about at a constant velocity, you might think that doesn't make sense because maybe perhaps if I have a car moving along a road and then I take my foot off the accelerator pedal, you might say, well, there's no force being applied and yet it's going to slow down. But actually, of course, there's things like air resistance and friction with the floor, which are going to slow it down. So there is actually a force there. If you had something in space, where there's of course no air particles, so maybe if you pushed an object out of your space station into the depths of space, you wouldn't need to turn on the thrusters to keep it going. You could just give it an initial push, and then there would be no more forces acting on it, and it would just keep going at that constant velocity. The second law he came up with is essentially F equals ma, force equals mass times acceleration. The way that he defined it was slightly more complicated than that. It is rate of change of momentum, but that's more of the sort of physics definition that we don't necessarily need here in A-level maths. But we can use it as F equals ma, force is mass times acceleration. And then his third law was that every force is an equal and opposite reactive force. So the most obvious case for explaining this is when you are stood on the floor, you are putting a force on the floor, but also the floor is putting a force on your feet to keep you there. Because if it wasn't, then you would sink through the floor. Just like if I lean on a wall, I'm putting a force on the wall, but the wall must also be putting a force on me. Because if it didn't, then I would just fall straight through the floor, or fall straight through the wall. So every force has got an equal and opposite reactive force. And with these three laws, we can solve quite a lot of problems in mechanics. Okay, just to get us thinking about forces and to train us up a little bit about how to label a diagram, I've got a car here, lovely orange colour. The car is accelerating at 2 meters per second squared to the right, and its mass is 1,000 kilograms, so 1 ton. What forces are involved? So I'm just going to label the acceleration. And normally for acceleration, I label it as an arrow with like a double arrow on it like this. And I can write A, it's 2 meters per second squared. Okay. Its mass is 1,000 kilograms. Now mass is not a force. Okay. The way that we would turn mass into a force would be to consider its weight. Now weight, I suppose in our everyday lives we use weight in kilograms, but strictly weight is a force and weight is measured in newtons. So we said before that F equals ma, force is mass times acceleration. Weight is the mass times the acceleration due to gravity. Which we learned in the last chapter was equal to 9.8 meters per second squared. Okay. So here we can label it as 1,000, which is the mass, times 9.8. Okay, so that'd be 9,800 newtons of weight. We could also label it, instead of using the 9.8, we could just use the letter G, 1,000 G. Okay, we quite often do that instead in mechanics. So next time someone asks you how much you weigh, give them an answer in kilograms, and you'll annoy them. Now, other forces that are involved. If it's accelerating to the right, so maybe the driver's got their foot on the pedal, there is some sort of force forward. I'm going to label this as T. This could stand for maybe thrust, or it might stand for attractive force, but I'm just going to label it as T, some sort of force forward. There's also going to be some forces backwards. There's going to be perhaps air resistance. I'm going to write that as AR, air resistance. And there could also be friction between the tyres and the road. Okay. There could be other forces as well. Maybe there's like a sideways wind on it, and there could be all sorts of other things. But those would be the main forces that I would put on here. Some sort of forward force on the engine. Things like air resistance and friction, we might combine these two into one force. And then it's weight downwards. There's one more, remembering Newton's third law about there being an opposite force. So if there's 1,000 Gs downwards, there must also be a force upwards from the floor. Because remember we said otherwise the car would sink through the floor. So there's also a reactive force upwards, which must be equal and opposite. So that's also going to be 1,000 G. And what we call this reactive force is we call it the normal reaction force. Okay. The reason we say normal is because it acts at 90 degrees to the floor, 90 degrees to the surface that you're on. Okay. If I wanted to write an equation here, I could use F equals ma. So if we consider the forces to the right, and we just think about all the forces that are going right, I can use F equals ma. So my forces would be T minus air resistance, and it's a minus because it's obviously trying to go left, that force, minus the friction equals ma. So that would be 1,000 times its acceleration to the right is 2 meters per second. And for instance, if I was given T and I was given the friction, I could work out air resistance and other combinations like that. But that would be the starting point for writing an equation. And this is what we call resolving forces, is considering the forces in a particular direction and either adding them or subtracting them, depending on what they're doing. Okay, here's a more basic example where we've just got an object. Okay, so this object weighs 2 kilograms, and it says it's accelerating to the right at 2 meters per second squared. We can see that its weight has already been labelled for us as 2g newtons. There is some sort of forward force of x, and then a resistive force left of 4 newtons. We've got to find y and x. Let's first of all resolve the forces. Actually, we're going to do to the right first, I think. We'll do it in the direction that it's moving first of all. So resolving to the right, I've got force x minus 4 newtons. And that equals, because remember here I'm using F equals ma, 2 times the acceleration to the right is also 2. So x is going to be 8 newtons. If I want to resolve in the other direction to find y, so if I'm resolving vertically, then I would have, if I do F equals ma again, y minus 2g equals 2 times, now its acceleration up and down is 0. I know its acceleration to the right is 2, but up and down it's 0. It doesn't tell me that it's accelerating up and down. It's not lifting off the floor or anything like that. So A is just 0 in that direction. So this means that y is 2g, or 2 times 9.8. Okay. Let's have a look at another one. Okay. Same sort of idea. This time our object is accelerating to the left at 2 meters per second squared. We've got the weight of 4 kilograms, so its force downwards is 4g. We've got a force to the left of 80, a force to the right of x, and we've also got an extra force downwards of 20 newtons. I'm going to resolve left first of all, which is the direction it's accelerating in. So I've got 80 newtons minus x newtons, and that equals mass times acceleration. So that's 4 times 2, because it's going 2 meters per second left. And then I can solve this. So I've got 8 minus 80, and times minus 1, so 72 newtons for x. If I now resolve up and down, so I've got y is up, so that's going to be a positive y, minus 20 and minus 4g. And that equals ma, so that's 4 times, in this case, 0. It is not accelerating up or down. And now I can solve this. So y is going to be 20 plus 4g, so 20 plus 4 times 9.8, which is 59.2. Okay. Just to make a point about which direction I resolve in, so left or right or up and down, if I was going to redo this calculation here, okay, but instead I was going to look at the forces to the right, then I would have x, because that's going to the right, so that could be positive x now, minus 80, and that would equal m4. Now the acceleration, because it's accelerating left at 2 meters per second squared, and I'm considering things to the right, I would consider that acceleration to be minus 2 because of the directions. And then I would still get x equals 72 newtons. So it works either way around, as long as you manage your signs correctly. Okay, here's a more worded question rather than just a diagram. So a particle of mass 5 kilograms is pulled along a rough horizontal table by a horizontal force of magnitude 20 newtons against a constant frictional force of magnitude 4. Given that the particle is initially at rest, find the acceleration of the particle. So first thing we do in mechanics is just draw a diagram to make this clearer for us. Okay, so there's our object. It weighs 5 kilograms. It's pulled along a rough table by a horizontal force, so there's a force this way of 20 newtons, and a constant frictional force, so trying to stop it, of 4 newtons. We can also label the weight on here, so we've got a weight of 5g, and we'll have a reaction force R, which in this case is also going to be 5g, assuming that it's not lifting up off the table or anything like that. So part A is find the acceleration. So it's obviously going to accelerate to the right because 20 is bigger than 4. I'm just going to label it as A for now. So resolving my forces to the right, I've got 20 minus 4 equals 5a. Just using F equals ma. So that's 16 equals 5a. So a is 16 over 5, which is 3.2 meters per second squared. Okay, so that's the first part done. B, the distance travelled by the particle in the first 4 seconds. So we're looking for a distance. We've got a time, 4 seconds, and we've actually got an acceleration. So hopefully you've twigged that this is going to be a SUVAT question. So we're looking to find S. We've been given T is 4. We've just calculated A as 3.2. And it also said, given that the particle is initially at rest, so we could say that U is 0. So S, U, A, and T, so it's going to be S equals UT plus half AT squared. And then we can solve this. So that's just going to be 0.5 times 3.2 times 16. So the distance is 25.6 meters. Okay. Part C, the magnitude of the normal reaction between the particle and the table. Well, we sort of already did that in our diagram, didn't we? If the weight is 5g, the reaction is also going to be 5g, assuming that it's not lifting off the table. So the magnitude of that force is 5g, or 5 times 9.8, which is 49 newtons. Okay. Right, this question we need to carefully consider acceleration and directions is what I mainly want us to think about here. So a small pebble of mass 500 grams, okay, that's 500 grams, they're not 500 g, so 0.5 kilograms, is attached to the lower end of a light string. Find the tension in the string when it is moving upwards with an acceleration of 2 meters per second squared. So let's draw this diagram first. So we've got a small pebble of 500 grams, so I'm going to label that as 0.5 kilograms. And it's attached to a piece of string, okay? And there's a tension in the string. And it says it's moving upwards with an acceleration of 2 meters per second squared. So I'm going to label this like that. The force in the string is pulling it upwards. So there's a force here, T. The other force which is involved is going to be its weight. So that's 0.5 g, or 0.5 times 9.8. And now I can resolve my forces upwards. So that would be T minus 0.5 g equals ma, so that's 0.5 times 2, because the acceleration is 2 upwards in the positive direction. And I can solve this to find t. So I get 5.9 newtons. It's the tension in the string. For part B, we've got the same scenario, but it's moving downwards with an acceleration of 3 meters per second. So I'm going to draw the diagram again. And this time it's accelerating. Well, so it's moving downwards with an acceleration of 3 meters per second squared. So this is my scenario. The tension in the string is still upwards. Okay, a piece of string is not going to force your object downwards. A piece of string attached to the top is always going to be trying to basically stop it falling. So the tension goes upwards. And we've still got the weight of 0.5 g. Now when we resolve, I'm going to resolve, it doesn't really matter which direction you do it as long as you do it accurately. If I resolve upwards, then I could have t minus 0.5 g equals 0.5 times, now because the 3 is going downwards and I'm resolving upwards, this would be times minus 3, which then gives me t equals 3.4. If I wanted to resolve downwards instead, so perhaps I wanted to resolve in the direction that it's moving, the equation would be 0.5 g minus t equals 0.5 times 3. And I would still get the same answer. Okay, still going to get that 3.4. So as long as you consider your signs accurately, you'll still get the same answer. Okay, let's do the last two. In part C, it's moving downwards at a constant speed of 5 meters per second. Let's draw a diagram. So t is still going upwards, it's still got its weight of 0.5 g. Now read what it says carefully here. We've got a constant speed. It's not giving us an acceleration, it says there's a constant speed. If that's true, constant speed means that acceleration is 0. So it's not accelerating. It doesn't really matter what its speed is. It's not accelerating. That's what's important. So if I resolve my forces upwards, then I will have t minus 0.5 g equals 0.5 times 0 is the acceleration. So that just means that t is 0.5 g. So t is 4.9 newtons. Okay, you could, if you know that something's not accelerating, you might be able to jump straight to the step where you say that t is 0.5 g, because you could say that the forces are balanced. So you could go straight to that point. Part D. I'm just going to draw the diagram again. So I'm always labeling tension as up because a string attached to the top of something is never going to push your object further down. Okay, it's always trying to stop it falling, basically. Now, scenario D, it said it's moving downwards with a deceleration of 4 meters per second squared. So it's moving down, but it's actually getting slower and slower and slower. Okay. So if that's true, so we could say that it is accelerating this way, but we could say that A is minus 4. That's one way of thinking about it. So it's accelerating downwards, but it's getting slower as it does that. So then A would be minus 4 downwards. The other way we could interpret it is by labeling it as 4 upwards. So I could draw the same diagram. But instead of A equals minus 4 downwards, I could say, well, that's equivalent to it accelerating upwards at A equals 4. And if we resolve this, I'm going to go for this first example, I'm going to resolve upwards. T minus 0.5 g equals 0.5 times, if I'm resolving up, it's accelerating at minus 4, then that would be 4. Okay, because I'm resolving up, but it's accelerating downwards at minus 4. So that'd be times 4. So 0.5 times 4 plus 0.5 times 9.8. So it's going to be 6.9 newtons. On this one here, if I wanted to resolve, well, if I resolve this one up, it would be the same one, but I could resolve down as well. But either way, I'm going to get that 6.9 newtons. Okay, accelerating down, but decelerating would be minus 4 in this direction. But that's exactly the same as accelerating upwards with 4. Okay. Now, for some questions to do for practice, I'd like to have a look at exercise 10C. Lots of questions about resolving forces left and right and up and down and using F equals ma. If you get stuck, obviously use the work solutions. Those are very useful in mechanics for seeing what equations did they actually come up with for the scenario to then solve.